How's it going, everyone? Today we're going to talk about Unit 4, Lesson 5, which is on intermolecular forces of attraction. So, intermolecular forces, just like they sound, are the forces of attraction between molecules, so intermolecular, between molecules. So we're going to talk about the different types of intermolecular forces, which of course we're going to learn is based on the polarity of a molecule. So let's get started. So first, a quick definition. So as it says here, intermolecular forces of attraction are forces of attraction between molecules, and these forces can vary greatly, but are generally weaker than the bonds that join atoms in molecules, ions and ionic compounds, or metal atoms in solid metals. Now, what that means is when water molecules break apart from other water molecules, they do so keeping intact the entire molecule. So when we boil water, we're not separating hydrogen and oxygens that are covalently bonded together. Instead, we're separating one complete water molecule from a second complete water molecule. Okay, on the screen, you can see some different types of attractive forces. So the very first one are called London dispersion forces. Then below that, we have dipole-dipole interactions. The third one listed is hydrogen bonding. Now, numbers 4 and 5 are not really intermolecular forces of attraction. That's why they have the little asterisk there. We'll talk in depth about what is meant by ion dipole forces and network covalent bonding. What I do want you to notice is in the table on the right side, you'll see that nonpolar molecules, and a lot of these are diatomic, so H2, O2, Cl2, Br2, you're going to see they tend to have very, very low melting points. Negative 253 degrees Celsius for hydrogen, negative 183 degrees Celsius for oxygen. These are extremely low melting points and boiling points. The second one that's listed here are polar covalent molecules. Again, these are molecular compounds. And in this case, you're going to notice slightly higher melting and boiling points. So now we're talking about only negative 88 degrees Celsius or negative 33 degrees Celsius. We start to see more numbers that are in the positive portion of the temperature scale. When we go up to ionic compounds, you're going to see these are much higher boiling points. So these are extremely strong bonds, and same thing for metallic where the boiling points are even higher. So let's begin by talking about London dispersion forces. So first of all, as you can see here, they are weak forces of attraction that result from a temporary, that's an important word there, it's not a permanent, but a temporary buildup of electrons on one side of an atom or a molecule. So if we look at a picture, you'll see that we have two atoms in this case. These are not necessarily molecules, but they could be. And what happens is that electrons are moving around in atom A. Atom A and B are both the same type. So let's say they're both atoms of neon. So we have a temporary buildup of electrons on one side of the atom. So as the electrons are moving around in their orbitals, suddenly we have a buildup that's temporary of electrons on one side. What that does is it causes the electrons in a nearby or adjacent atom to move to the other side, remembering that, of course, electrons will repel each other. So when they repel each other, this exposes the nucleus of this second atom to the electrons of this first atom. And as a result, there's an attractive force here known as a London dispersion force. This is temporary and only exists for a brief period of time, at which point the electrons then go back to their normal distribution in both atoms A and B, and they might form another temporary dipole with a nearby atom. So let's take a look at the second part. So for nonpolar molecules, these are the only attractive forces that are present. They do occur in polar molecules as well, but they're the only type of attractive force in between two nonpolar molecules. And if you look at the list of, this is just the halogens in group 17, if you notice at the top of a group where the atoms are small, the molecules are gases. But as we go down a group and the atoms get larger, you start to see that they go to a liquid state and then eventually to a solid state. So what this tells us is that London dispersion forces are really weak. But when we have a large enough molecule, they do become slightly stronger. So London dispersion forces are very much related to the size of the atom or molecule. Larger molecules and larger atoms are going to have stronger London dispersion forces. As I note in my last point there, the force of attraction increases as the size of the atom or molecule increases. And then here's just another example here, this time with the noble gases. So this is looking at molecules, this is looking at atoms. You'll see the same trend. So as we go from helium to krypton, small atom at helium, large atom at krypton, you'll notice the boiling point increases. Our second type of intermolecular force of attraction is called a dipole-dipole interaction. Dipole, di meaning two, so two poles. So this is the interaction that occurs between polar molecules. So dipole means having two poles, so a positive pole and a negative pole. So intermolecular force of attraction between the positive end of one polar molecule and the negative end of an adjacent molecule. In this picture, you'll see I've chosen hydrochloric acid or hydrogen chloride molecules. So if you notice, the negative side of hydrogen chloride is attracted to the positive hydrogen side of an adjacent molecule, a nearby molecule. Same thing here, negative side where chlorine is attracted to the positive side where hydrogen is. Dipole-dipole forces are stronger than LDF. That's why polar molecules have higher melting and boiling points in general than nonpolar molecules. Let's take a look at our last type of intermolecular force of attraction, and that's called hydrogen bonding. This is really like a special case of dipole-dipole, a really strong version of it. So the force of attraction that exists between a hydrogen atom of one molecule and either a nitrogen, oxygen, or fluorine atom of an adjacent molecule. This is usually present only when the hydrogen is bonded using a covalent bond, an intramolecular bond, to the highly electronegative atom. So let's take a look at an example. Here we have water. You'll notice that the hydrogen atom of one water molecule is attracted through this hydrogen bonding to the oxygen of an adjacent water molecule. This partial negative on the oxygen is caused by a sharp difference in electronegativity between hydrogen and oxygen. Oxygen, if you remember, has an electronegativity value of 3.5, and hydrogen is just 2.1. The force of attraction that we see in hydrogen bonding is even stronger than what we saw in dipole-dipole and LDF for molecules that are similar in size. Again, you're going to hear that come up a bunch. So when we're comparing strength of forces, we're going to justify that by saying we're comparing molecules that are relatively similar in size. So what I wanted to do on this slide was to just summarize for you the different types of polarities that are associated with different molecular geometries. So we're going to call every molecule either polar, meaning one side is more positive or negative than another, versus nonpolar, where everything's kind of equally distributed. So if we look at a linear molecule where both atoms that are attached are the same, we're going to say that that is a nonpolar force of attraction. If we look at something that is trigonal planar, again, we're going to say that that is nonpolar. If we look at something that we classify as bent, because of that odd pair of electrons that's not balanced out, we're going to say those molecules are polar. In fact, anytime that we have an unbalanced force, that molecule is going to be designated as polar. So going through the rest of them, tetrahedrals almost always going to be nonpolar as long as all four attached atoms are the same. Trigonal, pyramidal, and bent are always going to be polar. Just like seesaw and T-shaped planar will always be polar, but trigonal, bipyramidal, and linear can both be nonpolar. Keeping in mind, when we have something that is nonpolar, the only thing that we're dealing with is LDF. When we have something that is polar, then we have to consider dipole-dipole and possibly hydrogen bonding. I will show you how to go ahead and add these elements to your bonding and molecular geometry charts that we're submitting this week. the next force of attraction that we will discuss are ion-dipole interactions. Now, this is slightly different. An ion-dipole interaction is not just a single type of molecule. Instead, this is the relationship that exists between an ionic compound and a polar molecule. So in this case, the force of attraction between the positive or negative ion in an ionic compound and a second substance that is polar. And normally we're going to talk about water as being the polar substance. So water having a negative side and a positive side. You'll see that the water molecules will surround the ionic compound's ions in a very specific fashion. So the positive end of water will surround the negatively charged ions. So in this case, we're talking about chloride ions. And then you'll notice when we have the sodium ions, which are positively charged, they're surrounded by the negative side of water, the oxygen side of water. So in this way, a water molecule helps rip apart this ionic compound and then surrounds that ion, whether it's negative or positive, with the opposite charge. So the positive end of water with negative chloride ions, the negative end of water with positive sodium ions. This force of attraction explains why ionic compounds will dissolve in water. The last type of bonding that we're going to talk about today is called network covalent bonding. This is basically something that is completely different than what we've talked about earlier today. So this is a very specific type of bonding that occurs it occurs in many things, but we're going to only need to know about 4 of them. So this occurs when we have a web, like an interconnection of overlapping covalent bonds that are present, and they result in substances having very high melting and boiling points. So in this picture, you can see this is a picture of diamond. So we have carbons. Carbons, remember, form 4 bonds. So each of these carbon atoms is attached to other carbon atoms through this web of covalent bonds. The reason why it makes melting and boiling points so high is because it requires you to sever multiple bonds at the same time. So anytime that you have to do that, that's going to require a tremendous amount of energy. Thus, we're going to have very high melting and boiling points. So examples that I'm going to ask you to know are carbon, and carbon has 2 different allotropes that we're going to talk about. So carbon as diamond and carbon as graphite. Both of those will have very high melting and boiling points. Silicon dioxide is another one, and finally silicon carbide. Those are the only 4 examples that I'm going to expect you to recognize where network covalent bonding is taking place. Okay. On this very last slide of the presentation, I wanted to go over and kind of summarize for you the different forces of attraction and how strong or weak they are. So we're going to start by looking at the strongest forces here at the top. As we just mentioned, network covalent bonding is going to be the absolute pinnacle of that. So this is where we see very high melting and boiling points in carbon, things such as diamond and graphite. The next strongest force are ion-dipole attractions, and those are the interactions that occur between polar molecules like water and ionic compounds like sodium chloride. Again, very strong forces of attraction. The next type, now we're talking about intermolecular forces of attraction, is hydrogen bonding. So that's molecules that have hydrogen bonded to either NO or F. Then we go to a traditional polar molecule, and we have dipole-dipole forces. And then finally, the weakest forms of attraction, which are present in almost all atoms and molecules, are called London dispersion forces. And remember that those get stronger as we get larger atoms and molecules. Okay, at this point, I would like to go over how you're going to finish up this activity from last week and go over each of the columns that are near the bottom of the table. If you are watching and your table looks a little different because you're either in college and career prep or honors level, you probably don't have this first box here for hybridization. That's completely fine. For the accelerated honors students that are watching this, I'm going to go over in a separate video what to fill in for the hybridization box. Now, on to the bond polarity. When we're evaluating bond polarity, we're looking at individual bonds within a molecule. So for example, the bond between hydrogen and oxygen in this molecule. So I would write hydrogen dash oxygen to represent the hydrogen to oxygen bond, and then I'm going to put polar. Now, even though this is not 100% true, pretty much all of the examples in our assignment are going to end up being polar bonds. That's because there are different elements, and the difference in electronegativities is almost always greater than that 0.4, 0.3 threshold. So for all of our bonds, we can go ahead and put polar. When we evaluate the molecule polarity, so in this case, our molecule is water, so I'm going to write the formula for water. And when we're evaluating the polarity, what I would like you to look at is this combination of electron domain geometry and molecular geometry. And then go back to that slide in the presentation where I evaluated all of these for you. So we have a 4-2 bent, which is this one right here. So we're going to call that polar. So this chart in today's notes is going to be especially important to us in designating these as polar, non-polar, etc. So I'm going to write polar in this spot for water. And then, as we learned in the video, for anything that's polar, we have LDF, we have dipole-dipole, and now we're also going to consider this for hydrogen bonding. So to do that, ask yourself 2 questions. Do you have hydrogen? And is that hydrogen bonded to either nitrogen, oxygen, or fluorine? In this case, the answer is yes. So we will also have hydrogen bonding in this molecule. Let's take a look at a second example. In this example, we have carbon dioxide. So as you can see, we have a bond between carbon and oxygen. It's actually a double bond. We're going to again say that that bond is polar. In this case, we have linear and linear. So that's these 2 designations here. If we go back to our chart for 2-2, where we have linear. So 2-2 linear is this first example right up here, where we have non-polar. So in this case, we're going to list the molecule name or formula, CO2. However, in this case, because we have something that is non-polar, forgot to add that here. Because we have something that's non-polar, we have LDF, and that's the only thing that we're going to write down for non-polar molecules, LDF only. Okay, so that is how I would like you to complete the bonding and molecular geometry assignment. There's also a separate simulation on intermolecular forces that everyone is going to complete as part of the work this week. I hope everyone has a great week, and I will talk to you soon.